What if our best AI benchmarks are actually rewarding language shortcuts more than real understanding, while another model is learning to unify proteins, RNA, and biomedical context into one generative brain? In this episode, we dive into papers that challenge how we evaluate multimodal intelligence, push foundation models into biology's deepest layers, and even rethink diffusion itself by generating only the truly meaningful part of a symmetry space. From audio illusions to molecular design, the frontier of AI is getting stranger, sharper, and far more ambitious. Let's explore the first paper. All that glitters is not audio rethinking text priors and audio reliance in audio language evaluation. All that glitters is not audio argues that high scores on audio language benchmarks can substantially overstate true auditory understanding. The paper introduces a two-axis diagnostic: text prior, measured by performance with audio removed, and audio reliance, measured by how performance changes when the clip is split into equal segments and only fragments are evaluated. Across 8 LOMs, including audio, Flamingo, 3, Quen 2, audio, 7B, Quen 2, 5, Omni, 7B, Quen 3, Omni, Desta, 2, 5, Phi, 4, multimodal, and Voxtro Mini Tray B. On MMAU, MMAR, and MMAU Pro, models preserve 60-72% of full audio accuracy even in the none condition, showing that much of benchmark performance is recoverable from text alone. Text backbone baselines were also far above chance, exceeding it by 12.4 points on MMAU, 5.4 on MMAR, and 3.6 on MMAU Pro on average, indicating strong linguistic shortcuts in benchmark design. Temporal decomposition further showed that among items genuinely requiring audio, only 4.2% needed information spread across the entire clip. Roughly 96% could be solved from at least one local fragment. Item-level categorization into text solvable, audio needed, fragment sufficient, cross-segment, audio harmful, and unsolvable revealed that 26.239.5% of items were text solvable, while audio-dependent items were mostly fragment sufficient rather than cross-segment. The paper concludes that current benchmarks often measure a mixture of text priors and local acoustic cues, not holistic audio perception, and recommends reporting audio-free baselines and fragment-based reliance metrics for more reliable evaluation. Let's explore the second paper, Mimic, a generative multimodal foundation model for biomolecules. Mimic is a 1B parameter generative encoder-decoder foundation model that learns the joint distribution of biomolecular states across nucleic acid, protein, evolutionary, structural, regulatory, and semantic context modalities. Its core architectural novelty is a split-track transformer. Aligned signals on the same coordinate system are summed within nucleic acid or protein tracks, while unaligned text, context tokens are kept separate, with learnable register tokens, aggregating global state, and a cross-attention decoder reconstructing arbitrary missing modalities. Training uses stage context scaling from 1,000 to 10,000 tokens and to 25 modality-specific pathways on LoRe, a newly curated aligned dataset containing 12 97 mRNA transcript examples, 15 61 M proteins, 2 M aligned transcript protein pairs, 1, 64 M RNA chemical probing records, RASP2, 1, 67 M protein surface examples, massif, and is greater than 4B biomedical. Context tokens across is greater than 6,000 organisms. Across sequence completion, multimodal conditioning consistently improves reconstruction over sequence-only inputs. Mimic outperforms or matches specialized baselines on PFM bench and mRNA bench, with strongest gains on protein ligand binding, developability, RNA localization, and translation-related tasks. On mRNA bench, it reaches 0.475 AUPR for Go function and 0.789 for RNA localization, while a low-dimensional phyllo-P-based VP head boosts complex variant AUPR from 0.142 to 0.253 and Mendelian variant AUPR from 0.263 to 0.5. For splice prediction, Mimic exceeds Alpha Genome, Splice AI, and NTv3, reaching 0.905 AUPR on coding gene level and 0.701 on transcript level non-coding splicing when conditioned on TSS, TES. The same generative machinery supports constrained design. It proposes corrective RNA edits for the pathogenic HBBIVSII654C is greater than T-splice mutation without reverting the variant, generates diverse de novo protein binders. For PD-L1 and HACE2 with median TM score is greater than 0.85 and MACIF similarity is greater than 0.9, and predicts context-specific RASP2 reactivity that improves Vienna RNA secondary structure F1 by median plus 0.061 over sequence-only folding. Let's explore the third paper, quotient space diffusion models. Quotient space diffusion models formalizes diffusion generation on symmetry quotients, Q equals M divided by G, rather than on the full space, targeting the intrinsic state while discarding redundant group action degrees of freedom. Starting from a general SDE on a Riemannian manifold with a compact Lie group action, the paper derives an exact projected diffusion on Q, whose drift includes a mean curvature correction term, frac, sigma, T2, who, y, then lifts it back to the total space via horizontal lifts. This yields a sampler that is distribution preserving by construction, unlike heuristic alignment methods. The key training change is to supervise only horizontal components, that is to say, P, X, D, theta, X, T, X, unu, doi, L, so the network is unconstrained in vertical directions and no longer needs to predict arbitrary intra-orbit motion. For molecular generation, the quotient is instantiated as MAH3N, SE3. Translation is removed by centering the molecule at the center of mass, and rotation is removed by projecting away rigid body angular momentum. The SO3 horizontal projector and curvature term are given in closed form through a 3x3 inertia-like matrix K, making the method ON. Empirically, on Geome, QM9, and Geome drugs with ET flow backbones, the method improves ET flow by 9%, 23% relative and outperforms GeoDiff alignment and AF3 alignment across RMSD metrics. For example, on Geom, QM9, it reaches 96.4 coverage and 0.069 AMR on the equivariant ET flow setup. On protein backbone design with the 60M parameter, proteina, M, small, FS, quotient space diffusion improves designability from 96% to 97.6% at gamma equals 0.35, and substantially lowers distributional mismatch, for example, FPSD versus PDB from 386.5 to 274.7, while also beating a 200M proteina variant on most metrics. That's a wrap on today's AI paper highlights. Thanks for watching.